Today we're going to make the connection between the electrical potential and the electrical field. Keep in mind this diagram of the direct conversions you can make between different things. Between those things that act locally and which exist everywhere in space, and separately, those things that are more of a force-oriented concept, force concept, and those things that are an energy concept. Okay. So, for those that act locally, related to forces, well, the force itself. A force does not act everywhere in space, it acts on an object, which is at a local, it is at a particular place. That's what we mean by local. Now, forces are related to the electrical field, which does exist everywhere throughout space, but it's directly tied to the existence of the force. An electrical field creates a force at that point on an electric charge Q. So we can convert between force and electrical field. For that matter, for those things acting locally, on the energy side, we've also got the potential energy. And you remember that it is the change in potential energy with respect to position gives rise to a force. There's an overall negative sign there. So we can convert directly between these. Furthermore, the potential energy, which is a local concept, it is, after all, an object that has a potential energy. It's something that it possesses. So you have to have an object to have that potential energy, and an object must be at a particular place. But throughout space, there is the electrical potential, which we can convert directly from the electrical potential energy. Furthermore, we can convert between the potential and the electrical field and vice versa. So, we have ways to convert equations that relate each of these pairs. We don't, at least here, have ones that go diagonally across this. So if you want to go from potential to force, you'd want to go potential to potential energy to force, or potential to field to force. Either way would get you to the same result. Now, in order to find the potential from the field, recall first that we have a connection between potential and potential energy. Okay, where U is the potential energy of a charge Q and all of the other source charges creating the field that it finds itself in. And then we divide by our charge of that test charge, Q, that we're dealing with, which has that potential energy, or shares that potential energy, and we're left with the potential, which does not depend on the presence of that little charge Q. Okay. Now, the change in potential energy is therefore equal to the change in potential is therefore equal to the change in potential energy divided by Q. All right. Now, the change in potential energy. Now that we've got a change in, a delta in there, we can relate this to the work potential energy theorem. Change in potential energy of an object is equal to minus 1 times the work done by the electrical force. Again, in this case, we're assuming that the potential energy is going to be the electrical potential energy, so I'm not going to subscript it electrical. All right? And then this is W is the work done by the electrical force. Now, change in potential energy. This is for two different places. Maybe you've got a point there and a point here, and your charge moves from here to here, the starting point and the ending point. And however you move there, what's going to turn out does not matter. So we look at the difference in the potential between these 2 points. Delta V, delta U is the difference in potential energy between those 2 points, and W is the work done by the electrical field as it crosses this path between those 2 points. Okay, now, the work done by the electrical force is the integral of force dotted with ds. Both of those are vectors. So the dot product between those two as we go from point S1 to point S2 on this path. Okay. So that means, and this is another one of these that comes in from previous sections, so I'm highlighting it in blue. We put that together. Delta U is negative of this integral, f dot ds, from S1, S2. That's S1, that's S2. Okay. We put that in here. We have delta B is equal to negative 1 over Q, because that's 1 over Q there, integral from S1 to S2 of f dot ds. Okay, putting that all back in together. That's delta U there. Now, let's bring the 1 over Q inside the integral, and that will give us f vector over Q dot ds from S1 to S2. And if you recall, the electrical field is equal to the force, the electrical force divided by Q. Electrical force on a charge Q divided by the charge Q itself. So we are left with the change in potential from point S1 to point S2 is just equal to the integral of E dot ds between those 2 points. There. Find a red piece of chalk to highlight the answer. Now, the book, for reasons that will become useful later, also does the dot product and puts it in a form that they notate minus integral of E sub s ds, where you have no vectors now, from point S1 to point S2. We'll include that as well in our definition here. Now, E sub s is just, or I should say, E sub s ds is just the dot product of the vector E with the vector delta, ds. ds is an infinitesimal step along the way here. Like that. Now, this is a line integral. It's a kind of path integral. You're integrating across this path. And there are some rules that are a little tricky that make it a bit different from normal integrals. It turns out that it doesn't matter which direction you take the path. If you reverse it, your integrand becomes the same thing. Wait, let me think that I've said that correctly. There is an overall negative sign. So you have to figure out what the default positive direction is. So that's why the book puts it in this form, E sub s ds, where E sub s is then the component of the electrical field vector that is parallel to the path at that point as you're going along. And so they are effectively saying that don't treat anything where your angle between the field and your path direction is greater than 90 degrees. Don't get angles bigger than that, where your cosine of, say, 180 would be -1. Don't treat those. Just take the absolute value of any cosine that comes in from the dot product. This is something that I've worked out, tried to work out over some days, and couldn't come up with much of a better explanation than that for how you do these line integrals. Okay. And keeping that in mind will make an example the book does easier, because they flip a sign around without telling you why. And it's because of this. I wish they had given an explanation though. All right. Let's see, where are we? Okay. So, the potential difference between the points S1 and S2 is just -1 times the integrated electrical field over those 2 points, or the path parallel component of the electrical field over those 2 points. So, note that this means it doesn't matter what path you follow to get from S1 to S2. Because all that matters is going to be the endpoints. If you took that path to integrate, or that path, you get the same result, and you get the same result as this one. So in practice, it's easiest to choose the simplest path between the 2 points, not necessarily the straightest line. Perhaps, for example, if you have an electrical field, let's see, I'll use red for the field again. Let's say you've got a point charge here. The book's going to do this example. You know that the electrical field vectors point radially outward. They are strongest closest in. I'm drawing the field vectors, not the field lines. So I'm going to draw the length of the vector is going to be proportional to its magnitude here. Sort of. All right, you get farther out, and they get weaker. And so on. Anyway, let's say that we've got 2 points. 1 point here, and another point out here. So that's S1 and that's S2, for example. What is the potential difference between those 2 points? So what path would you choose? Would you choose a straight line between them? Well, you could actually. It might not be too bad. But here's what I would do. I would choose a path that goes perpendicular to the field line. So in this case, you're going in an arc of a circle until you get out to the this line here that goes straight in. And then, so I do this integral plus the integral going down this way. Now, in this case, you see your field vectors everywhere along this path are perpendicular to the path itself. So, the component parallel to the path is all that you're adding up, all that you're integrating over. And so at this point, along this path, this section of the path, the integral is 0. Now, when you go straight on in, all of your vectors are parallel to the path. And remember that we're going to be taking the fact that we've got the field pointing in a direction opposite the way we're going on the path doesn't matter. That cosine of 180 degrees, we just effectively we're taking the absolute value of that. And so then we're adding up the increasing field from these going in. This is the only part that contributes to the integral. Okay. Let's see here. And generally you're going to put in a functional form for the electrical field, E, as a function of position, and then you'll put your path, S, in terms of coordinates, and then you're going to integrate over the coordinates. And of course you can break up an integral into a sum of shorter integrals of different segments along the path, and so you can do it, that integral plus that integral, and you choose these in ways so that things go to 0 or 1 or some other things that are very simple. And keep in mind that one of your comparison points may be at a distance of infinity. Okay. So, for example, here I've actually got to look at the book because I didn't do a good rewrite of it. Okay, so for a point charge, here are the field vectors. As you're getting farther and farther away, I should put other field vectors pointing out in different directions, of course. But I don't want to fill in everything there. Now, let's compare the potential at 2 points at a distance of infinity. Now, this is a symbol for a break in the paper, like a rip in it. And out here is a point at r equals infinity, right there, along this same straight radial line. And the second one is going to be at a point r equals capital P for the point. Actually, we never do even put that. It's just r. That's fine. R equals r. Okay. So, I'm going to erase a little bit of my derivation here. Delta V equals the integral of e sub s ds. I'll choose the form that's already taken the dot product in, from point S1 to point S2. So, delta V then is the potential at the first point minus the potential at the second point. Now, let's see, which way did I do it here? From, first point is infinity, so we're going along the path this way. V of infinity minus V at r equals, oh, and there should be a negative sign there, equals minus integral on infinity up to r at r, e sub s ds. Actually, this is going to be e sub r dr. So I put that in terms now of the coordinate. Okay. Now, here's the thing that the book does without any explanation whatsoever. And if you were doing this, you probably wouldn't even bother to do the step, and then you'd wonder why you got the wrong sign. This is set up correctly. This is set up logically, I should even say. And you're going to wind up solving for, oh, hold on a second, hold on. I've got it written around incorrectly here. Delta is always final minus initial, right? So it's at point S2, which is R, minus the point S1, which is infinity. Okay. Now, the book does this little trick where they reverse the order of the limits, which gives an overall negative sign, or it multiplies the integral by -1, which is a positive sign. So they go from R out to infinity of this stuff here. They don't say why to do that. Now, if you didn't do that, and you were thinking in terms of the direction dr, which is pointing inward along your path, you think, and the field that points outward, and you take the dot product, and you've got a minus sign in there. You're going to wind up with a sign error. And so the book flips this around and just says, oh, yeah, now we're going from R out to infinity. Why don't we do that way to begin with? This is why line integrals have a couple of little tricky bits that aren't generally well explained. But I think what's best, if you keep in mind that going in the direction opposite the direction of the field there, if your path is going inward like this and the field is pointing outward like that, we're not going to have an overall negative sign. And they reverse that just so that you don't do that. But they don't tell you why. Okay. So, I'm not going to do that. Let's see if I wind up with the wrong sign at the end or not. Okay, so E, the R component of the electric field is Q over, actually is there a Q? There is Q. Q over 4 pi epsilon naught times 1 over R. Nope, 1 over R squared. Okay. Now, I've separated the constants here from the variable R there. So if I put this in, I can pull the constants outside the integral, minus Q over 4 pi epsilon naught, integral from infinity to R of, let me write this as R to the minus 2 dr. Now, this means that we're dealing with power. We integrate that. We have R to the, let's see, we add 1, so minus 1 times the, let's see, the new exponent, which is minus 1. So we get an overall minus sign, which gives us a plus sign. Sorry, we multiply by an overall negative sign. So we get plus Q over 4 pi epsilon naught. Let's see, we've done that. We have R to the minus 1, so that's 1 over R, evaluated from infinity up to R. So, plug in for R first. Minus what we get when we plug in R equals infinity, Q over 4 pi epsilon naught 1 over infinity, which of course shrinks down to 0, to nothingness. Okay, so potential at R equals, let's add V infinity to each side, 1 over 4 pi epsilon naught, Q over R plus potential at infinity, which again we're going to set to 0. There. So, doing the line integral, Dr. Hamilton's easy line integral method, which is more or less right, we come up very simply with the answer here. We just did the integral and found that we had a 1 over r minus a 1 over infinity term, which went to 0, and we're left with the correct answer. Okay. Now, where do we get electrical potential from? Electrical potential arises from separation of positive and negative charges. So, any separation of positive and negative charges creates a difference in potential. Separation of charges, which means separation is delta S. S is some path that they're separated by. And you can see that if you say the potential at the positive side minus the potential at the negative side is equal to minus the integral from the negative side to the positive side, or where the negative and positive charges are, integral of E dot ds there. So you have to have a separation, a sum of infinitesimal ds's separating those charges there. How do you separate charge? You have the mechanical methods and chemical methods. Those are the two that I'll talk about today, but there may be others. For mechanical methods, you are physically carrying a positive charge from here to here, or a negative charge from here to here. The effect is the same either way. Shuffling your feet across the carpet will rub electrons off and will build up positive charges on one, actually I forget if it's on your shoe or the carpet, and negative charges on the other, and then when you walk over to the doorknob, you get a spark there. Because the doorknob is at a different potential than your body is. Your body, which has all of this excess charge on it. And you go up to the doorknob, and then some of that charge jumps across the gap there. What's actually happening with the spark is that the dielectric, the insulation of the air itself breaks down when the potential gets too strong across it there. Sorry, when the field gets too strong, when the potential difference is too great over too short a difference. There's a strong field, and you get a breakdown and a spark. Okay. Chemical methods would include, say, a chemical battery, whether it's a dry cell battery that we're used to putting in, or the wet cell battery that we've got in the car. Dry cell batteries are the kinds that you buy in the store and put in electronics, and the wet cells are in the car. All right, well, let's go with the mechanical first here. A rather spectacular method is the Van de Graaff generator. despite the tough-to-spell Dutch name, he was actually an American. Van de Graaff came up with this back in the early 1900s, and it's a way of moving charge and accumulating it in a steel dome. Let's see here. We've got a base here, an electrical outlet. Now, so we have a source of electricity, and we have a motor with a rubber belt attached to it. Okay. The motor makes the belt run around like this. Now, we strip off electrons from the belt by attracting them to a metal cone. And the sharp points on this metal cone have a very strong field. I'll explain why later today. And we pull those extra electrons off the belt then, leaving a net positive charge on this side of the belt. The motor carries it up to here, where a metal dome accumulates them. They add up there by means of another metal cone. I don't think you actually need the cone or want the cone touching the belt. It simply has to be very close to it there. Okay, so then the charges get off of that and spread around the metal dome there. And then, of course, in practice, we have a glass or plexiglass insulating tube surrounding the belt for just to hold it all together. Now, these can wind up building up a potential difference between here and then the outlet of hundreds of thousands of volts. Demonstration ones can do 500,000. I've seen them sold like 300,000 to 500,000 volts. It's not a whole lot of current. Not a whole lot of charge actually goes there, but the potential difference is enormous. And I have one here. Okay, so here's one. Now in this case, instead of a motor, I've got a hand crank, like that. I don't want to crank it up too much because my hand is up fairly close to it. This wand is plugged into the base then, and it is going to be held at the opposite potential. So if the dome up here collects a positive charge, this will have a negative charge on it. Okay. Now let me see here if I can show more of it more easily. Pardon me. Okay, that's not too bad. All right, now, if I sit here and start charging this, the longer I run it, the more charge builds up. I can feel the hairs on my arm standing up now because they're building up a charge in the field around this. Now, I'm not sure if you actually see the spark in the light behind us there, but cringing just a little bit because until that first spark, I never really know when it's going to go. And every time that discharges, I can feel the hair on my head having been built up a bit, then deflating a bit. Now, why does my hair feel anything? Well, take a look at this. I'm going to have to raise the camera again. Okay. Now, watch this here. Let's get the shade strong. Okay. Now, if you can see those, yeah, all right, they're showing up. Those little pieces of yarn sticking up. The reason they're sticking up is because they're all gaining a positive charge from the dome, that their base is conductive, and so it's at the same potential as the dome is. And so each of those pieces of yarn gain it, and so if they've all got the same charge, then they repel each other. And that means they have to stand up against gravity. Look what happens when I discharge the dome. They collapse back. Not surprising. All right, let's do that again. Now watch what happens as I move the wand around, which has a negative charge to it. They are attracted to it here. If I let it touch any one of them, they exchange charge and deflate. I say deflate, you know what I mean though. See if I can get a visible spark here. I'll turn the lights. I'm about to turn the lights off. All right, last demonstration for this. A bunch of piping. There. Now, these wind up getting the same charge, so they're all attracted to me, I guess. And actually, I will do one last thing, and I'll say about this with the lights off. Okay, I don't know how well it will focus with this dim. All right. Okay, I think these are starting to show up now. What you're seeing there, by the way, the visible spark is actually the hot gases in the air. And so there's the spectrum of the air itself. Now, something that will become important and in the last section of this chapter, or a later section of the chapter, there's a little screw on the top of this here. If I hold it over that, listen to the regular, very small discharges. Okay. Enough of the fun there. I'll say also that another mechanical method of separating charge is a volcano. As the ash comes out of an erupting volcano, it drags along, electrons are stripped off, and it picks up an overall static electrical charge. And so this is why you often see lightning bolts in the air around an erupting volcano. The presence of this lightning is one way that we have of inferring that there are active volcanoes on the planet Venus where we can't see the surface. But we've seen what appear to be lightning flashes in specific places where there are volcanoes, and we didn't know if they were extinct or active. The presence of this lightning might be indications that they're active. Now, for a battery, chemical methods. The book doesn't say it, but I'm going to refer to a cell and a battery, where in a lot of books, especially older ones and hobbyist books, the basic chemical electrical generator we're talking about is called a cell, a voltaic cell, because Volta was the one who worked on this. If you hooked up several cells together, you would get a battery of cells, or just a battery. These days, you often hear just the battery referred to, whether it's one cell or many cells. But I'd like to keep in mind the both terms. All right. In this case, you have a chemical reaction that separates the charge. Now, these reactions are between a chemical called the electrolyte and a metal. You have two different metals stuck down into it. And so the chemicals in here eat away at this metal and transfer electrons over to here, or vice versa. And so you're physically moving charge again, just like in what I call the mechanical methods, except that it's a chemical reaction that is doing the moving of the charge, rather than you picking them up and moving them yourself. But the result is the same. Now, in both this case and the Van de Graaff generator, you have to do work, because if this is let's say this is a positive terminal, and that's a negative terminal. Now, they're made out of metal, keep in mind, and therefore they are conductors. So if we move electrons from here over to here, so the electrons are moved over this way through this chemical bath. Now we've got an excess of electrons over here, which means we have an excess of we have a net positive charge over here on the positive terminal. In moving the electrons, you're moving them from a place where they had been neutral to a place where you have more electrons. Now, like charges repel. So the electrons already there exert and create an electrical field around them, which repels the incoming electrons. So the chemicals have to do work to overcome the electrical force that wants to repel them. Just like in the case of the Van de Graaff generator, the motor, which was physically moving the positive charge up the belt to a region that already had an accumulated positive charge in the dome, that accumulated positive charge created a field which tried to repel the incoming positive charge. So you had to do work to move them from that point to that point up there. So, between the positive and negative terminals, there is a difference in potential energy, which is equal to -1 times the work done by the electrical force. Now remember, if you move a charge from here to here, and there is an electrical force trying to push it the opposite direction, the electrical force still does work, even though you've moved it against the force. Now that work is going to be negative, of course. You are doing a positive amount of work to move it in a direction it doesn't want to go. The force is going, the electrical force will do a negative amount of work because you're overcoming it. All right. Now, we know that delta V is change in potential energy over Q. So, Q delta V is the change in potential energy. So that in here, so we get Q delta V equals negative work done by the electrical force. Oh, I want to put in one more thing here. The work done by the electrical force is opposite, minus 1 times the work done by the chemical reactions. So, work done by the chemical reactions, W sub chem, there, all right, divide through by Q. So the work done by the chemical reactions divided by Q is the change in potential, electrical potential. Now, we're going to define this as the electromotive force of the battery. Electromotive force, which is script capital E. Must be capital, must be script. Or lowercase e m f. Not pronounced inf, just EMF. The book hates using the term electromotive force, which is what that stands for, because it sounds like it's a force, which you would think because of the word force there. But look at the units. These are not units of force here. You know, work, which is energy divided by a charge, does not get you units of force. So they're wanting you to kind of move away from the idea of calling it electromotive force. So the term came about a long time ago before we really standardized some of our language in this. I think it's perfectly fine. Just don't think of it as a force. But it relates to the ability to move charge there. So we will define EMF, script capital E, as the change in potential between a battery's two terminals, which is therefore the chemical work per charge. How much work the battery took to move any one individual charge from one terminal to the other, divided by the charge itself. That gives you the EMF, which is also the difference in potential between the two terminals. So let's say here we've got V sub plus, and here we've got V sub minus. That's delta V. Unsurprisingly, this is measured in volts. So, if you have a AA battery, which is 1.5 volts, that is the electromotive force of that battery. Almost, just about. The reason I say almost is that there are some losses. We don't get out all of this. This works in an idealized battery. In practice, we lose a bit. Some of that work comes to nothing. We get waste in the battery. And so the measured amount is going to be somewhat less than this. Nevertheless, we'll deal with the idealized versions of batteries for now. Okay, now, and if you have a bunch of batteries and you add them in series, then you just add up their EMFs, their potential differences. So delta V in series equals delta V of battery 1 plus the potential difference between the terminals of battery 2 plus the same for battery 3 plus so on like that. Now what does it mean in series? That means if you've got a positive terminal and a negative terminal on that battery, number 1, that's battery 2, and positive and negative on battery 2, positive and negative on battery 3, and so on. Then you string a wire from the negative terminal of battery 1, connect it to the positive of number 2, and from the negative of 2 to the positive of 3, negative 3 to the positive of 4, and so on like that. You don't connect positive, 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 and negative, negative, negative. And that would be adding them in series, parallel. That's adding in series. Now, when you're putting them into a battery holder, you're going to put them end to end, pointing the same way, like this. Where the tab that sticks up is the positive end of the battery. Like that. That's in series. Okay. Well, that's all well and good, but you know what? Really, the value of having the potential is that we can find the electrical field from it. The potential is a much easier concept. It's a much easier thing to deal with. Part of the reason is that it is not a vector. So, and potentials add. So if I've got some charges lying around and they create an electrical potential, a potential field even, all right? You can, the potential exists throughout space. That's when I say a field. It's not a vector field like the electrical field is, but it is a field in that there is a value of the potential at every point in space. It's a scalar field. It just has a magnitude. There's no direction to the potential. If I keep adding charges in sources, all I have to do is to add in their potential equations, functions, fields, drawings, and just add them all together. Then, the electrical field can be found very simply from that combination of all the potentials. So this is what we're going to do now. Finding the electrical field from the potential. Okay. Let's let a charge Q let's see. Here's a charge Q. It's moved a short distance, delta S, from here to here. Now, since it's a very short distance, then the electrical field is roughly constant between the 2 points. And so the starting and stopping points have a small potential difference. So the potential difference between the starting and stopping points is delta V, of course, which is delta U over Q, the change in the charge's potential energy divided by the charge itself. This is a general equation there. We've already known that. It applies in every situation. But now, since the difference is very small, we have moved a small difference. Really, let's say that this is an infinitesimal difference, ds. So since the difference is small, this is in general. Now we let the small, that finite non-zero difference in potential delta V, let's shrink it down to just dV. Delta U is the infinitesimal difference du. So now we've got dV is du over Q. So the same thing still holds, even for an infinitesimal, infinitely small difference. Now, what about du? We want to get this in terms of the work done to move the charge between those 2 points. But, in general, recall, for a macroscopic change of potential energy, delta U, there was an amount of work done minus W. Now that's the total work to go a fixed distance, delta S, there to there. All right, work done by the force, accurately. And that work was the integral of the force dot ds, where ds is an infinitesimal vector along that line there. But if we want just an infinitesimal, one of those little infinitesimal steps along this macroscopic path delta S, one of those infinitesimal steps, we're not adding up the sum of all the infinitesimal steps, we're just taking one. So the infinitesimal difference in potential energy along that infinitesimal step is just F negative, here, F dot ds. We don't have the sum, the integral, adding up all of the others. Right. Okay, I hope this makes sense here. If it doesn't, think of it through. If we integrated up du, we would get delta u. We integrate, and then we would integrate this side, which is the integral of f dot ds, the negative side of it. All right, but I was trying to work that backwards to see, because you knew this relationship here. Okay, now let's put that in here. We have an infinitesimal bit of work in the form of f dot ds. So dv is equal to minus f over q dot ds. So I put du in here. In fact, let's put that in the form, let's take the dot product and take f sub s ds over q. So the component of force along the path. Now, F over Q is the electrical field, and we're taking the S component of it, the component parallel to the path. So it's minus E sub S ds is equal to dV. And now if I divide both sides by ds, and a minus 1, then I've got negative dV by ds is equal to E sub S. And I hope that is actually visible over the badly erased chalk there. So, the S component, S remember is the direction of the path, the S component of the electrical field, E sub S, is equal to negative dV by ds. I'm going to rewrite that up here where it's clear. What is this? Well, this is minus 1 times the slope of potential along that path. So, the electrical field points in the downhill direction. Whichever way the potential is decreasing, that's the direction the electrical field points. The more steeply, the more quickly the potential decreases, the stronger the field will be there. And if there is no change in potential over some region, then there is no electrical field there at all. So, note that we must take a derivative of the potential along the other directions to find the electrical field components on those directions. So, ultimately, you might wind up doing a derivative along each coordinate direction to get each component, vector component of the electrical field. But if you can use symmetry, you might be able to find a direction or an axis that the electrical field must be parallel to. And if the field is parallel to that direction, it has no components in the other directions. In that case, your perpendicular components then are all going to be zero. Okay, as an example, let's say we're given a point charge. Now, let's find the electrical field of a point charge. The radial component from this of the electrical field must be negative dV by dr. That's from what we just derived. We know that the potential of a point charge, V sub pt for point, is 1 over 4 pi epsilon naught Q over R. And we sub that in for V. So, minus, let's see, I'll pull the constants out front. That's Q over 4 pi epsilon naught. Minus Q over 4 pi epsilon naught times d by dr of the variable, 1 over r. Well, that's, what is that, negative 1 over r squared? Gives me a positive Q over 4 pi epsilon naught. Let's make it 1 over 4 pi epsilon naught times Q over r squared. And that's the radial component of the electrical field of a point charge, which is exactly what we knew it was. And we came up with that in 2 steps. Okay, so that's not bad. Okay, now, continuing with this, let's see, so where the potential changes the fastest, the field is the strongest, and where the potential contour lines, those are the equal potential lines or equal potential surfaces if you're in 3 dimensions, where those contour lines are the closest together, the potential changes the fastest, and therefore strong field. Where the equal potentials are spaced far apart, then you've got to go a long distance before the potential changes very much, and you've got slowly changing potential, and therefore a weak electrical field. Along a direction, ds, with constant potential, so dV equals 0, the electrical field has no component on that direction, and vice versa. So, if we look at a point charge, again, let me draw the equal potential lines first, because those are the easiest things to do. They follow the symmetry of the charge. They'll be spaced close together, close to the charge, and they'll be spaced farther apart, farther away. So the field is changing fastest when you're closest to the charge. There. So here you've got a very high potential, lower, 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 something like that. So from most positive to the most negative. Now, when I say most positive, most negative, what about the numbers, say, 7 and 2? 7 is the most positive of those two, and 2 is the most negative. It's not a negative number, but it's the closest to being the most. It's the opposite direction of being positive. That's what I mean when I say that. Now, the field lines must be perpendicular to the equal potential lines. So, you've got V1, V2, V3, V4, V5, and so on, different equal potential lines. The spacing tells you how quickly they're changing. So the vectors must point radially outward, perpendicular to them, from high potential to low potential, and they must be at right angles to the one that they're attached to. Now keep in mind, the electric field vector has a length that depends on the magnitude of the field, the strength of the field. And it may cross other equal potential lines, but it's not at those points. It's only at this point. But it just has, we have to draw it somewhere. Okay. And you get farther out, and the field gets weaker. You get farther out still, the field is still weaker, and so on like that. If you were to draw this as a three-dimensional, what might be called a relief map, topographical map, with the charge at the center, let's see, you draw it as a sharp-pointed feature Okay, I'm trying to draw a shading on here, which works to some extent. Now, the equal potential lines are just contour lines on this, slices at different levels here. So potential increases upwards, and then you've got coordinates, say, x and y. The field lines went radially outwards. The magnitude is given by how steep the potential graph is there. If I come farther down, it's less steep. Come farther out still, much less steep. And so on. Okay. And if you have some more complicated case, if I draw the contour lines, the equal potential lines again, what if we have a case like this? Now, who knows what kind of case could make field lines like that. But if this is V minus your most negative one, and that's V plus your most positive one, the field lines, the field vectors must point perpendicular to them at each point. The farther apart the lines are, the weaker the field is. But here they get closer together, so the field is stronger. Here they're really strong. And so on like that. And if you were to connect up field lines instead of field vectors, then you know that you've got to make a smooth connection perpendicular through each one of these here, from positive to negative. Like that. Okay. Now, to find the complete electrical field vector, break it down into components. Maybe it's in Cartesian, for example. So E is the sum of E sub x I hat plus E sub y j hat plus E sub z k hat. each one of these components is just the derivative of the potential along that direction, times minus 1, minus dV by dx, I hat, minus dV by dy, j hat, minus dV by dz, k hat. And that's it. Okay, now, I said earlier that the path taken through an electrical field doesn't matter for certain things. The difference in potential between 2 points does not depend on the path you use to get from one to the other. For that matter, you don't even have to get from one point to the other because the points are there and the potential is there at both points. And so it can't depend, the relative differences in potential between those 2 points can't depend on how you decide to walk between them because they are what they are without you even doing the walking between them. This brings us to Kirchhoff's loop rule. Along any closed path. That's a complete loop. The final and initial points have to be the same. The sum of all the potential differences along that path add up to 0. And therefore, the potential difference along that loop, the total potential difference, is 0. Another way of putting it, if you sum up all the individual little potential differences of every step along the path, that adds up to 0. Or, even better yet, if you integrate over it must be closed, starting at any point's the same, that's what that symbol, the closed loop, means on the integral symbol. Of all of the infinitesimal differences, dV, they add up to 0. That's Kirchhoff's loop rule. Now, if you keep in mind a vision of the potential as like a topographical map, an elevation map of terrain, then you should not have a problem with this. So if you've got regions of high and low potential, maybe there's a point like source here, and then there's a wire here, something else. Some region of low potential in between them. Trying to shade them like the hillsides and such. Okay. And if I pick a point here, and I want to move a charge around, I mean, what do I even mean by a path? I can imagine that I'm moving a charge around the path and experiencing different potentials along, or different fields along the way, different potential energies and so on. But really, the potential is what's there. And so if you go along and you're integrating over a path that goes up over like this and down there, and then up over here, and around behind, and go back over this way, and back to that, you wind up at the same point you started at. Well, potential on this is the height. And clearly, you're at the same height you started, so there's no difference in potential along that path. And if you take another path, which goes over here, and then over that little hump, and then here, and then over that little hump, and then that, and then it climbs up this mountain from the backside, and down to here, and up to there, and down like that, and then over, you still wind up in the same point where you started, and only the beginning and ending points matter anyway, and therefore the difference in potential between the beginning and ending points is 0, and therefore the sum of all the differences of potential along every step of your path add up to 0. This is also a statement of the conservation of energy, because if a charge, Q, is moved along this complete loop, its net change in potential energy must be delta U equals Q delta V. You recall that from earlier. So over this loop then, net change in potential energy is Q times the net change in potential. I've already told you that's 0. So if it comes back to where it started, its potential energy will not have changed, and therefore it has the same potential energy. This must be true because the potential energy depends only on your current location, not on your history, not on anything else. Doesn't depend on your velocity or other things like that. Okay. Next, we'll go over the case of a conductor in electrostatic equilibrium. Hold on just a second. Give a drink of water. All right, now, remember that electrostatic equilibrium means for a conductor that all of its charges are at rest. They've reached an equilibrium position where they're happy and they're not going to move anywhere else unless you change things. So, while there are any charges moving, you are not in electrostatic equilibrium. Recall that this means that all of the net charge that the conductor has, if it has any excess of charge, either positive or negative, all of that net charge has to be on its surface, not in the interior. And therefore, there must be 0 field everywhere inside the conductor. Two important things. Now, since the electrical field is 0 for all points inside the conductor, then the change in potential, which is equal to negative E integral of E dot ds from point S1 to S2. All right, look at the potential difference of 2 points inside the conductor. Since the field is 0, this means the difference in potential between any 2 points inside the conductor is also 0, which means that since there's no difference, V is constant. Inside a conductor in electrostatic equilibrium. This is an important result. So all points inside the conductor are at the same electrical potential, whatever that potential happens to be. That means the conductor's surface is an equipotential surface. It forms a contour line of potential. Now, since we know that the electric field is always perpendicular to the equipotential surfaces, the contour lines, then the electrical field immediately outside the conductor must be perpendicular to the conductor's surface. And this is exactly the same conclusion that we drew several lessons earlier from a physical argument on the fact that it would otherwise be making charges move if the field were not perpendicular at that point. But now we've arrived to it from a simpler way. Okay. So therefore, field is perpendicular to surface of the conductor. Now, the field can vary along the conductor. You can have regions of strong field and weak field. How can you tell? Well, take a look at a conductor of sort of an irregular shape here. Drawn it as a polygon. Cross section of an electrical conductor. Hunk of metal. It's charged up with some potential. It has an electrical field in it. We can figure out the strength of the field by approximating the corners as being circles of larger or smaller size, or spheres of larger or smaller size. The gentler the angle, the more open the angle, the larger this imaginary circle is. The smaller the angle, the smaller the circle is. There. In that sense, very, very tiny circles are like sharp points, which is really true because all things that we have, all the matter around us, is really made up of atoms in practice. Atoms are effectively round. And we have sharp-bladed knives and things like this, which are really made out of a collection of very round but very small objects. Okay, in geometry, these might be called the osculating circles, that osculating from Latin to kiss, because they just touch, kiss, are tangent to the lines at these points here and here. So you can draw circles on both sides. Now, why does this relate to a circle at all? Recall from equation from section 28.6, the potential outside of a charged sphere is the same as the potential away from a point charge. Sphere of radius capital R, and you're the distance lowercase r from it. Now, we learned that you can write the potential is capital R divided by lowercase r times the potential at the surface, capital V R. How do we relate this to a field? Now, a field is -1 times the derivative of v with respect to our coordinate, r in this case. So, that is negative, let's see, capital R, capital V naught over lowercase r. Capital R, capital V naught times d by dr of 1 over r. That gets us negative 1 over r squared, so we get a positive r v naught over r squared. So, that's the field outside of the charged sphere. The field then, that'd be the r component, at the surface of that sphere is equal to, so I said the coordinate equal to capital R, so divided by capital R squared, so it's equal to V naught over capital R. Now, this means E is proportional to 1 over R. That means the more, the gentler bending surfaces, the broader corners, are like spheres of very large radius, which means the field is weaker there. The sharp corners are like spheres of small radius, so the field is stronger. I'll say dull corner leads to a weaker So what would it be like for this? Well, along a straight surface, a flat surface, the field, remember, must be perpendicular to the surface at every point. It's pretty evenly spaced out. Now, you get near a corner, the field lines start crowding together a bit. It's, if you imagine them being like on the surface of that sphere now, I'm taking approximations, of course. Like that. Around a more sharply curved corner, they crowd even more. Sharper still. And they have to blend into the ones that are not crowded like. And then the really sharp ones, like that. Now, furthermore, this means, since the field is stronger in these points, there must be more charge there. So the charge density is highest at the corners. And it's weaker on the smooth, flat surfaces. This is the origin of the debate over the proper shape of a lightning rod that was held in Benjamin Franklin's day. Benjamin Franklin had, when he invented the lightning rod, I believe that he had made sharp-pointed ones. Now, the electrical knowledge was still primitive at that time, so I don't know exactly how much he understood mathematically about this. But you can get an easier discharge and a lower voltage from a sharp point. And so he designed the sharp points then, because then that would be, he figured that the lightning would be most likely to jump to that sharp point. Here's the ground. Here's a house, and here is a sharp-pointed lightning rod. So, you've got a cloud up here, field lines pointing out. Not sure if the clouds are positive or negative, so forgive me for a moment. And if you have, the thing is, you want it to discharge at this point and not somewhere else along the house. So you want the field to be stronger here. And so now it doesn't attract lightning from miles around. It only, if you would want to say, attracts lightning to this point more favorably to the point right next to it on the roof. It's not like it has an influence that spreads a long way around. Okay, but the house itself is also has field lines coming down to it. So then you get if the field strength becomes great enough, then you get a bolt of lightning down to that point, and the idea is that you have a good gauge wire that conducts that down into the ground, which is at a reference potential of 0, what we call ground potential. By the way, the English, this is around the time of the American Revolution, and some of the English scientists were claiming that Franklin's idea of sharp-pointed lightning rods was really an American plot to endanger the life of the King of England should he put up a sharp-pointed lightning rod. And so they were advocating round, ball-shaped rods at the top. And some also tried coming up with a compromise, which was a ball with a spike pointing out of it. So that's as it was. Okay, final point for today. And that is that if I draw, let's say I've got a couple of conductors, in this case a sphere, plate. Held to a potential difference. So let's say the sphere is held at one terminal of a battery and set at 0 volts, and the plate is held to positive 80 volts, just because I picked that number of contour lines. Now, the equal potential lines, the contours of voltage, of potential between them, are going to imitate the shape pretty closely of the conductor's surfaces themselves when they're right around them. Let's see, 1, 2, 3, 4, 5, 6, 7. So, but it's influenced by the presence of the other conductor. So ones that are right around both of these, pretty closely, I'm going to take the shape there. Notice these are at a potential difference. So that's 1, 2. Okay. So the next equal potential lines are a little more rounded. You have to have, if I space these equal potential lines out, remember they're contours, enough to go from 0 to 80, and I space them every 10 volts. I'll have another line with the surface counting as 1 for each of those. So I've got 0, this is going to be 10 volts, 20 volts, this is going to be, let's see, that's 80, that's 70 volts, 60 volts. So they have to, at the midway point, it's got to be the same for both. It's like I am unwrapping the surface of this conductor and then wrapping it inside out around this one. They gradually morph in between to the two different shapes. Okay, so let's see, 30 volts. $40 volts. Now let's see, I'm going to jump over here to 50. And then 40 volts is exactly in between. Looks like it should split the difference there. There, like that. I think you can see fairly intuitively that this, those work pretty well. Notice that on the side facing away from the other conductor, the equal potential lines get spaced out very widely, because I've got to, as you go to the next equal potential surface, you've got to cover a lot of distance wrapping around like this. But in between them, you're going from 0 volts to 80 volts in a short distance, so they're very closely spaced together. And that means the field is stronger there. The field is weaker going out this way, because it's a long distance to go out this way and around, following the being perpendicular to the equal potential lines at every step, and get the same potential difference. So, if I draw a field line starting on the more positive, ending on the more negative. Now, these are complete lines, not the individual vectors. But they've got to be perpendicular to both the surface, which is an equal potential surface, and the equal potential lines at every point. These here are a little more curved, you see. Okay. And I think that I've covered everything I had to say about that. There you go.